This is GMATS 41. You are welcome to our physical chemistry class. In this video, we are going to look at the topic Ionic equilibrium. You would recall that in our previous classes, we already treated chemical equilibrium where we introduced the concept of the law of mass action. Do you still remember that? What is the law state? Okay, you want to tell us that? Alright, now we would recall that the law said that the rate of reaction is directly proportional to the active masses of the reactant. Is that not so? Talking about the active masses, we can actually use concentration to replace them. So the rate of reaction is also directly proportional to the concentration of the reactant. That was actually the law of mass action by Goldberg and Wahage. Now, that law can be applied to both chemical equilibrium, where you deal with compound reacting, and you can also apply it to ionic equilibrium, where our interest is the reaction between ions, or perhaps a compound dissociating to give us an ion. The first attempt to study the law of mass action applied to ions was first put forward by Ostwald in 1888. Ostwald, and the law that he proposed, is that okay, is known as the Ostwald Dilution law. We're going to derive that law, is that okay? Now, this law is actually used to apply the law of mass action to weak electrolytes. You want to take note of that. Just consider this reaction on the board. This is an electrolyte AB. AB is dissociating. You know, when a compound produces a ion, we refer to that process as dissociation process, right? You can also call it ionization process. It dissociates to give us ions. Is that okay? So, this electrolyte dissociates to give us A and B, positive ion and negative ion. If we assume the concentration of the electrolyte to be C in moles per liter or moles per dm cube, and then we refer to the degree of dissociation, that is the rate at which the electrolyte dissociates to give us the ions. If we refer to that rate as alpha, what is not going to happen at equilibrium? You know, the concentrations for normal reaction, when the reaction is just starting, you know, and the concentration at equilibrium, they are not the same. At equilibrium, the concentration is such that the reactants are reacting to give you product, and at the same time, the products are reacting to give you what? The reactant. So at equilibrium, we're going to get the concentration of these species in this reaction to be this. Concentration of the electrolyte AB will be equal to C minus C alpha. C alpha now is the portion of the concentration of the electrolytes C that have dissociated, that have removed, been taken away from this AB concentration, right? So we're going to say that concentration of AB is equal to C minus C alpha, and we can factorize the C is common, so you can write the equation in this form, right? Then at equilibrium also, since we know that the electrolyte is giving us C alpha, then if you look at the product here, this is 1 mole of this ion, 1 mole of this ion. It means they're going to get equal value of what the electrolyte is giving off. Is that okay? It therefore means that the electrolyte giving off C alpha, then the concentration of the positive ion is going to be the C alpha. It's going to appreciate. It's going to increase by C alpha. That of B will also increase by C alpha because the number of moles are the same. So here now we know the concentration of the reactant, we know the concentrations of the product. We can now apply the law of mass action to determine what is otherwise known as equilibrium constant, as we encountered when we discussed chemical equilibrium, right? So if you want to get the equilibrium constant, do you still remember the formula for Kc? Product of the concentration of the products divided by the product of the concentration of the reactant. So it's just simply products divided by what? Reactants, their concentration. Of course, raised to the number of power of the number of moles. The power of the concentrations will be the number of moles of the reactant species and the product species. So if we actually write out the equation, our Kc will be equal to, you multiply the concentration of the product divided by the concentration of the reactant. You can see them here, right? And then we can work on this equation. We know concentration of A positive and B negative. That's the ions. You can substitute them here. pick them from here, C alpha times C alpha, divided by concentration of the electrolyte, AB, which is giving us C, 1 minus alpha. Now if you look at this part of the equation, C times C give us C squared, and then alpha times alpha will give us squared alpha, divided by this. You notice that this concentration will cancel one of the concentration in the numerator. Therefore, we have that Kc is equal to alpha squared times concentration divided by what? 1 minus alpha. So this equation is very, very important. It is a corollary to that equation you saw for Kc in terms of concentration when we dealt with chemical equilibrium. Kc here is known as ionization constant or dissociation constant for the electrolyte. And it depends on temperature, so it's constant at constant temperature, and when temperature changes, its value will also change. In the next video, we are going to derive the Ostwald dilution law. We now want to look at the Ostwald dilution law from the equation we derived previously that the dissociation constant is equal to the square of the degree of dissociation alpha times the concentration of the solution divided by 1 minus degree of dissociation. We derived this equation previously, right? So now, we want to look at the situation where 1 gram molecule of an electrolyte is dissolved in V liters of solution. Now, if we dissolve 1 gram molecule of electrolyte in V liters of solution, we can write an equation for molar concentration. We know that molar concentration is equal to number of moles divided by volume. So, if we're not dissolving like 1 mole, alright, that's 1 gram molecule in V liters of solution, you see that this concentration equation will now become 1 over V. Is that okay? Because N is 1. And we have this equation here. This V is known as dilution, that's what it's called. And we can substitute for concentration here using 1 over V. If we substitute for concentration here with this equation we have, this is what we are going to get. Multiply square of alpha by 1, and then you get this equation. So the dissociation constant being equal to square of the degree of dissociation divided by 1 minus degree of dissociation times the dilution, which is V, volume, is the Ostwald dilution law. So this formula or equation very important, okay? That's the Ostwald dilution law. Now, having said that, let's assume that we are dealing with weak electrolyte. You know that an electrolyte can be strong, it can be what? Weak. However, we're going to limit our study to weak electrolyte because that is the main concern of Ostwald. He attempted to study what happens in weak electrolyte. Now, for weak electrolyte, this dissociation, degree of dissociation alpha is far, far less than 1. You know, weak electrolyte, the degree at which they dissociate, the degree of ionization is small. Is that okay? Therefore, it means that this 1 minus alpha would be approximately equal to 1 because alpha is far, far less than what? 1. We can neglect that degree of dissociation alpha from this denominator term. And once we neglect it, then it means that 1 minus alpha would be approximately equal to 1. Multiplying it by V, you still get only V in the denominator. That gives us equation 4. And you now see that from equation 4, we can now calculate the degree of dissociation alpha for a given weak electrolyte. And as you see on the board, from this equation, if you cross multiply and take square roots of both sides, then our degree of dissociation will be square root of the constant of dissociation, that is dissociation constant times what? The dilution. This equation 4a is the equation for calculating degree of dissociation for weak electrolyte. And in words, we can simply state that the degree of dissociation is directly proportional to square root of what? Dilution, V. Because here, our Kc, which is dissociation constant or ionization constant, is constant at a given what? Temperature. Let us walk through this question on the board. Okay, there are 2 of them. We have to calculate the hydrogen ion concentration in a 0.2 molar hydrogen cyanide, that's HCN, solution. We're giving Ka for HCN to be 7 times 10 raised to the minus 7, okay, minus 10, right? 7 times 10 raised to the minus 10. Please take note that the Ka there is the same as Kc, that is the dissociation constant or ionization constant. The second part of the question, from question 1, the percent ionization of hydrogen cyanide is? We don't know, so we want to find out. We want to get a value and see what that would be. So let's walk through this and see. We are calculating the concentration of hydrogen ion. So I'm going to write that. Let this represent concentration of hydrogen ion. We don't know. Then the concentration of the solution, that is concentration of HCN, was given to us, and that is 0.2 molar. Then we know our Ka value, which is the same as Kc, that is 7 times 10 raised to the power minus 10. So the first thing we have to do is to write the dissociation equilibrium reaction for hydrogen cyanide. Okay, so let us write that and see. Hydrogen cyanide undergoing dissociation will give us hydrogen ion plus cyanide ion. Now, we already established that at equilibrium we have what we call equilibrium concentration. Is that okay? Equilibrium concentration. And we said that, okay, if you have the electrolyte and the concentration of the electrolyte is C, at equilibrium it will give out a part of it. Alright? That part that will be lost is C alpha. So it's going to be C minus C alpha. Then the product will get that quantity that was lost. So you could see that will give us C open bracket 1 minus alpha. Because if you have C minus C alpha factorized, this is what you will get. Then this hydrogen concentration will gain this value of concentration. This will also gain the same value of concentration because they have equal number of moles. So if you look at this, we know this C, concentration of the electrolyte, HCN. We don't know the degree of dissociation. So let us find the degree of dissociation first. But degree of dissociation in terms of concentration is given as Kc all over the concentration. You know, you can also get it in terms of what? Volume. We actually derive it as degree of dissociation to be equal to the square root of Kc times the dilution V. But we didn't have the dilution here. What we have is concentration. And you know that concentration is 1 over what? Dilution when dealing with Ostwald law. So that's why we have this equation. And then if we substitute our Kc, which is the same as Ka, is 7 times 10 raised to the power minus 10, divided by 0.2. The degree of dissociation, if you walk through this, K 7 times 10 raised to the power, that's going to be 5.9 times 10 raised to the power minus 5. Now that we've gotten the degree of dissociation, alpha, we can now calculate the concentration of the hydrogen ion. So let us calculate that and then say that concentration of hydrogen ion will now be equal to, look at the formula, Kc alpha, so that's C alpha, and that will give us 0.2, we're multiplying by 5.9 times 10 raised to the power minus 5. If we work through that, the concentration of hydrogen ion is going to give us 1.18 times 10 raised to the power minus 5 molar. Let's take a short break. When we come back, we'll look at the second part of the equation.